I'll be brief this time before I go finish some classical mechanics homework. But I promise you all at least a brief on some quantum mechanics today. So we'll get a little some of that in. And let me make sure this is looking good. It's looking okay. So one of the concepts we went over recently is the concept of the expected value. So I'll show that briefly because it actually sets the foundation for a lot of things that will be coming in the future in quantum mechanics. So it's showing pretty well. So the idea is that in quantum mechanics is all about positions. So with the positions as far as probability. So we can have either a momentum or position. That's what we start with. It'll get more complicated later. But what we can do is we can actually get the expected value or the average value for a position because in quantum mechanics we don't necessarily um, we can't define the precise position of a particle and its momentum at the same time. So we have to sort of pick one to allow it to be the one that we focus on that we can get the most accurate data on. So, for instance, a position graph might look something like this if the position is very definite, and this place will be the most likely place to find the particle. And as it goes away from there, it'll peter out to zero. But generally, this area here will be the most likely place to find it. And still, it would have to be a situation where if we took an integral of this over infinity, it would still have an area under this curve of 1. So it will be something like integral negative infinity to infinity. And we have the, uh, you could say, average of the wave function of the particle. And we're integrating this over x. And this will have to equal 1. So to make this more specific, let's say that we had a wave function. This is basically the probability density of how likely you can find a particle in a certain place. Let's say we had the probability density f of x equals 2x. So this will be 0, this will be 2, this will be 1, and let's say our a and b is from 0 to 1. So our probability density has a range from 0 to 1 on the x-axis, where it has a value, and all else 0. So if you wanted to find the expected value of this, so basically this is a simplification of what it would look like with an actual particle, but it just gets the concept across. Basically what we do is we take the probability density function and we're going to integrate it over the range that it has a value. So maybe a particle in space somewhere might go to infinity, but here we know it's from 0 to 1. This is A, this is B. And I'll put my f of x in there, just like we have the probability density here. And to get the expected value, I have to also add an x, which is the value that we want the expected value of. So it'll end up being 0 to 1 x 2x dx, which equals the integral 0 to 1 2x squared dx. So when I take this integral, I'll end up with 2x third over 3 integrated from 0 to 1. So it's going to be 2 thirds. So given this probability density function here and this range, and the range is set up, by the way, so that the integral over the entire range equals 1. So let's test that out as well. That means it's properly normalized. So let's go 0 to 1, 2x dx, and see what we get. So this will be 2x squared over 2, 1, 0. So that's going to be x squared, 1, 0. So that's 1 minus 0 equals 1. So two details, the probability density function, when you integrate over everything, has to equal 1, then it's properly normalized. So this means that you have a 100% probability of finding a particle somewhere. What's going on, Real Kindness? Glad you can make it. So this probability density means that there's a 100% possibility of finding a particle somewhere. And just reviewing this some of the basics of quantum mechanics, like we discussed last time, Kindness. And this will set the foundation of things that we'll do later as far as understanding quantum mechanics. And hopefully, I sound more even. I changed my mic so that even when I'm talking down, it should pick me up about the same volume. So we'll see how that works when I listen back, but it should be better. So this probability density of this uh, uh, particle, I guess we can say, it is normalized because when I integrate over the probability density itself over the entire range that the particle should exist. So this is the range that the particle exists. Anywhere outside of there is 0. The fact that when I integrate this, I get 1, that means the function is properly uh, normalized. So that means I can go ahead and take an expected value of their probability density. One more basic thing here I'll do before I log off. I'll be brief this time, but I'll get some basic concepts here. A very, very important concept is the, uh, what do you call it? I don't remember the exact name. Standard deviation? I think that's the word. Standard deviation. Don't quote me on the exact word. It might be something different. But I believe it's a standard deviation. And that's going to be the square root of the expected squared value minus the expected value squared. It's a tedious deviation, derivation. So I'll maybe come back another time and do the derivation, but it's a pretty tedious derivation. But what this is basically saying is if I have a distribution of probability of finding a particle, and let's say this is uh, let's say the expected value here, the standard deviation tells me the probabilities at certain increments away from the average. So this first would be the first standard deviation on either side. This would be two standard deviations and so on and so forth. So it's very important as far as error margins and things like that. So any scientific paper, even if you look at the presentation I did on the last debate, you saw I had a plus and minus at the end. Generally, that plus and minus at the end is one standard deviation. So generally, you kind of look at this width as one error margin on I guess I should say here on one side. This will basically be one standard deviation of error from what may be the actual value, which is the average. The closest we can get to the actual value is the average. So if we want that standard deviation in quantum mechanics, what we'll do is we'll take this same equation and instead of putting an x there, it will be the same thing. You use the same equation, everything is the same, but now you put an x squared there. And it'll still be the same f of x, the same probability distribution. So then I'll plug everything in. I have x squared 2x dx. So that's going to equal 2x cubed dx, 0, 1. So when I integrate this, it's going to give me uh, x to the 4th. Then I'm going to have to divide by 4. So 2 divided by 4, that's going to give me 1/2. And it's going to be same bounds. So that's going to be 1/2, right? So that's going to be the expected squared value, right? So we have the expected value is 2/3 from earlier. We have the expected squared value is 1/2. So since the standard deviation is the square root of the squared value minus the expected value, all squared, that's going to be the square root of 1/2 minus 2/3 squared. So that's going to be the square root of 1/2 minus 4/9, or the square root of 9/18 minus 8/9, excuse me, 18. So that's going to be the square root of 1/18. So that's going to be one standard deviation. So the idea is that if I found the particle, let's say I did a measurement, an actual experimental measurement, and let's say I found the particle on the x-axis, let's say at, I'm going to pick a random number. Let's say I found it at 2.1 over 3, let's say. Now I will put plus or minus 1/18 for the error margin. And this might be a bad value, I just guessed the number, but this is where generally, at least one of the ways that the plus or minus comes from, one standard deviation. But generally in quantum physics, in the theoretical side, like in classroom, we don't generally do this when we're, calculating this, but in like experiments, when you're actually doing real live experiments, then you have to do something to get the error value. If it's not a standard deviation like this, there's other ways to do it. I actually hate error calculations, but you got to do it. I'm starting to like it more because I know how to do it now. But when I first started, I was like, damn it, but I had to do everything. It's getting better at it. It's awesome. But that's all I have for today. I was going to keep it brief, but I wanted to make sure I showed up since I had a schedule. Because I have a vicious, what do you call it, classical dynamics homework that's due in, 2 hours and 45 minutes. So, okay. So you're saying right now it's fluctuating? Oh, we'll have to look at that then. I'm glad it's still better than last time. But maybe I should have booked my update. Okay. Thanks. I'll check it out again and I'll update it again and see what's up. But I'm glad it's still better than the first mic. So awesome. So tomorrow I'll be back for, what do I have tomorrow? Oh, I'll be discussing sort of basic physics on the regular channel. I believe somebody wanted me to talk about the shape of the Earth and seeing the Earth from certain distances away. And somebody else had another more complicated one. Awesome. So I'll work on it. I still got to get used to how this. What I need to do is just move the mic when I write and just move it back up. Maybe that's what I need to do. Let me see here. So that's probably what I'll do. I just move the mic down when I'm writing, and then it'll sound like I'm sort of talking into it here, and just move it up when I'm talking straight. And I'll figure something out. I'll get it worked out to make sure it's getting better. But they always say audio is the worst thing to fix when you're doing any kind of streaming or video or anything, and I think they're right. It's like the hardest thing. But awesome. Hopefully you enjoyed this. You'll be able to look back and see if you missed the first part. It's important concepts because basically this format here and what we end up doing this with actual particles when we're solving actual particles. So I did it here with a regular, like just a regular f of x. But eventually our f of x will be that psi. That's what that's called, the Greek letter psi right there. Can you see my mouse? I don't know if you can see that. This is the Greek letter psi. And eventually we'll get to finding the expected value and actually using wave functions and things like that. So look for me next Friday and we'll continue some quantum stuff. I'll be back tomorrow on the other channel for some general stuff. Always good seeing your real cognites. Thanks for the input on the mic. I'll listen back and see what I can fix about it. and I'll see you next time.